Well, we're nearly finished with the concepts related to line integrals. And then there's one major set of topics to follow that in our closing weeks of the term. This is called Green's theorem. And if you recall, this is our notation for a line integral to calculate work done by a vector field over a particular curve or path. And this particular symbol indicates that it is a closed path, and also that it is traveled in the counterclockwise direction. So samples that would maybe apply would be, things that look like this. X and Y axis. So if you were to travel from here to here, and then horizontally back to the Y axis, and then vertically down, that would be a closed, or the textbook calls it a simply closed region, traveled in the counterclockwise direction. Again, it could be as simple as a circle. It doesn't have to be centered at the origin, but it could be centered at the origin. It could be something where there's a curved path to a place, and then you travel the direct route back. That these are all closed, and they're all traveled opposite of the clock, counterclockwise. So that's what this notation implies. Think circuits and electricity to maybe get yourself started. I also want you to recall that there's what I would say is a formula. If you're given the vector field and you're given the curve, this is equivalent. And we also learned that there's a differential form. First component dx plus second component dy. These are all equivalent expressions. And when it comes to evaluating them, you know that my favorite is this one. But when it comes to writing them, the math and science nerds out there will probably lean towards one of these, or perhaps even another option. Now, Green's theorem. If we have these closed regions, and this is stating the theorem, not proving or deriving the theorem, it's equivalent to a double integral expression, and the region would be these regions. Here, 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 and the body of the integral would be n, the second component with respect to x, minus m, first component with respect to y. We will not be deriving this theorem, but my students and others that are listening in, that's Green's theorem for evaluating a line integral of a simply connected or closed region. There's a lot more detail behind this if your diagram is more complicated. So again, don't disregard the textbooks in the building of the math just because it's inconvenient now. Remember, later it may still become a big deal. But for our class time, this is how much time I have to dedicate to where the theorem comes about. And before I close, because this is just to introduce the concept, let me just show you something. Let me just slide up a little bit here since the theorem is still visible. If that vector field has these components m and n, two statements. One is something I'm just going to observe. With a double integral, that means I can only have two variables. So I'll just put a little footnote here, two variables. For a three-variable problem or application, we'll see that in a few sections in our last series of topics. That's one of the things I wanted to mention. But if you have this vector field and it is conservative, then that means n with respect to x is equal to m with respect to y. That's the test for conservative vector field. And that means that n with respect to x minus m with respect to y would be 0. And if we use this theorem and we attempt to integrate 0, we will get 0. Think of this as a volume of some kind. If there's no third dimension, there is no volume. There's no volume. And that's what we had stated with the fundamental theorem previously, that if you start and end at the same point and you have a conservative vector field, then the work is equal to 0. So this is just another way to do that. So, calculate work in a closed counterclockwise loop. Green's theorem will be for cases where that closed loop or circuit did not have a conservative vector field. This is really to help us with the not conservative vector field examples. Until next time.